Hello everyone. Let's continue chapter 14 about heart. This time we're going to talk about hemodynamic. What is hemodynamic? Hemodynamic refers to a set of principles that governs your blood flow. Remember, the most important event in your body would be oxygenation. You need to get oxygen, and then after getting oxygen, you have to carry this oxygen, and carrying this oxygen only happens through blood flow. So therefore, blood flow really is the second most event in our body, because first we have to get oxygen through the lung and oxygenation, and then we have to carry it. Of course, for having blood flow, we need volume. Without volume, there is no flow. There is two different types of volume in our body. One is called stress volume, and the one is called unstressed volume. Stress volume is blood in our body that is under stress, and that is the blood in your arterial system. Unstressed volume, as the name explains, is a volume that is not under stress, and that is the blood volume inside the venous system. As you know, blood is going to get inside the artery, and then it's going to come inside the arterial. After arterial, we have capillaries, and blood from capillaries is going to come to venial, and it's going to go to vein and comes back to the heart. As you can see in this slide, when the blood leaves left ventricle inside the aorta is going to come down, it's going to branch off in many arteries. These are big arteries, and each one is going to go to different part of the body. For instance, we have artery that is going to take blood to the brain, or take blood to the heart, or take blood to the kidney, and so on and so forth. Out of 100% of the blood that leaves left ventricle, there is a specific percentage that is going to go to each part of the body. You don't need to memorize this one, but my point of showing this slide is that the vessels that come off from the aorta, they are parallel to each other. In other words, if this is the aorta, you're going to have branches coming off of aorta in each side. And as you can see, these branches, they are parallel to each other. The wall of arterioles are very well innervated with sympathetic nervous system, and they have alpha-1 receptors. And you remember, alpha-1 receptor is going to constrict the vessel. There are only a specific arteriole in our body that contains beta-2 receptor. And you remember, beta-2 receptor is a vasodilator. It's going to open up. Majority of arteriole are being innervated by alpha-1. In other words, sympathetic can close it off. Only the arteriole in the skeletal muscle has beta-2. And that makes a lot of sense. As we mentioned in the autonomic nervous system, when you're under stress, sympathetic is going to kick in. And sympathetic is going to shift blood toward your muscle. As a result, the vessels in the muscle must open up. Therefore, every other arteriole is going to close off because alpha-1, but they're going to shift it toward muscle, and muscle has beta-2 to open it up. The venial and the venous system also innervated by alpha-1. In other words, when the sympathetic gets stimulated, it's going to squeeze your vein and push this blood from vein inside the artery. That is called unstressed blood, and that unstressed blood is going to decrease, and stressed blood will increase during stress or the action of sympathetic nervous system. Now, that is going to bring us to the term velocity. What is velocity of blood flow? Velocity, by definition, is the rate of displacement of blood per unit time. What does that mean? How fast you can move blood from one location to another location. We use the same thing in the regular talking. When you say my speed was 60 miles per hour, you're talking about how far you're going to go in 1 hour. Here, I say the speed of blood is 2 millimeters per second. That means in 1 second, it's going to move from one point to another point, which are 2 millimeters apart from each other. The speed of movement of blood flow, the velocity of blood flow, depends on a couple of important things. As you can see here in this formula, depends on blood flow and the cross-sectional area. What does that mean, cross-sectional area? Let's take a look at this picture again. Here's my arteriole, here's my capillary. As you can see, we have lots of capillary. If I add up the diameter of every single capillary that I have here, of course, the diameter of all these capillary together would be much larger than this arteriole that give rise to this capillary. Let's take a look at this slide. Here's my big artery, smaller artery, here's my arteriole, here's my capillary. As you can see, the largest cross-sectional area happens inside the capillary. As you move toward capillary, the cross-sectional area is going to go up. We have millions and millions miles of capillary, and if you add those sectional area of each capillary, it's going to be huge. So why this one is important? Because as you can see in my formula, the velocity inversely related to the cross-sectional area. That means the speed of blood flow inside the capillary would be very small. Let's say if you go fishing, do you go to a river that water is going to come through very quickly, or you have a better chance to fish if you go to a river that water is going to flow slowly? Imagine that if water comes and goes quickly, you have no chance for catching the fish. In the same token, if the blood comes inside the capillary and go through the capillary quickly, how these cells outside this capillary can capture the oxygen? Blood should come inside the capillary and flow slowly, so therefore the cells can grab the oxygen or nutrition. We want the velocity inside the capillary to be slow. As a result, oxygen and nutrition can get out and waste or CO2 can come back inside the capillary. The second player for velocity would be blood flow itself. If you open a faucet that's attached to a hose, more water is going to come inside the hose. That means water is going to go faster. So the amount of water that comes inside the hose is going to determine how fast this water is going to flow. With the same token, if you put lots of blood inside the arterial system, blood is going to go faster also. So Q, or blood flow, if it's going to go up, the speed is going to go up. If the cross-sectional area goes up, velocity is going to go down. Therefore, velocity is greatest in the aorta. Why? Because aorta has the smallest cross-sectional area, but has the biggest amount of blood flow. When the heart pumps, when you say heart, again, I mean the left ventricle. When the left ventricle goes to contraction and push this blood inside the aorta, so of course, the maximum amount of Q, or blood flow, would be inside the aorta, and also aorta has the smallest cross-sectional area. So therefore, as you can see, Q is going to go up, A is going to come down, and V would be the maximum. So the maximum velocity is going to happen inside the aorta. I'm sure you remember from your physics study that to measure cross-sectional area of a duct or a pipe or a chamber, we use this formula, pi r squared 2. As you can see, when the radius goes up, the cross-sectional area is going to go up by power 2. So radius would be very important. So V is equal to Q divided by pi r2. When the radius increases, the velocity is going to decrease big time. In this diagram, here's one vessel, here's another vessel, and here's the largest diameter of this vessel. As you can see, when blood is going to go from this size of the vessel to this size of the vessel, or to this one, the flow is going to stay the same, or Q. The amount of blood that's flowing here is the same, 10 ml per second. So if I punch this number inside the formula, as you can see, the Q is the same. The A for this vessel would be only 1 centimeter square. This one is going to be 10, and this one is going to be 100. As a result, you can see here the velocity of the blood in this vessel is 100 times less than the speed of here, because the area is increased by 100 times. So velocity here is 10, velocity here is 1, velocity here is 0.1 centimeter per second. This is very important because that's exactly what's going to happen to our body. Blood is going to come to aorta, which has smaller cross-section area. Then it's going to go to a bunch of arteries, so now the total cross-section is going to increase. Then it's going to go to capillary, and that is going to increase dramatically your total cross-section area. But remember, the amount of blood that your heart is pumping out, or Q, is the same in every single level. So the Q in the aorta is the same as Q inside the big arteries, and is the same as inside the capillary. Now, since we talked about blood flow, let's describe what blood flow is. Blood flow is movement of the blood from point 1 to point 2. The flow of the blood depends on two things. One is the difference in the pressure. If point 1 and point 2 has the same pressure, let's say pressure here is 10 and pressure here is 10, there's no need for blood to move. Why blood is going to move from this point to this point if the pressure is the same? Blood always moves from higher pressure to lower pressure. So if you want your blood moves, you have to have a higher pressure at the beginning of this vessel. You have to have a lower pressure. The second parameter that controls your blood flow is resistance. When the resistance of this vessel goes up, then less blood is going to flow. So therefore the formula would be blood flow is equal to difference in the pressure divided by R. Clearly, if I want to increase blood flow in this vessel, I have to either decrease my resistance or I have to increase delta P. Let's say I want to increase blood flow to my brain. How can I do that? I cannot change delta P in my vessels in the brain, but what I can do is changing the R. How? If you dilate this vessel, of course, by opening up the vessels, the resistance is going to go down. The more you're going to close the vessel, you're going to increase the resistance. By changing the size of the vessel, you can change the R. So vasodilation is going to decrease the R, but vasoconstriction is going to increase the R. Is this the only factor that changed the resistance? The answer is no. The resistance is related to length of the vessel, eta, which is the viscosity of the blood, and R, which is radius. As you can see in this formula, the most important player would be radius because it's a power 4. If you change the radius of a vessel, if you just change this size of vessel slightly, the resistance is going to change dramatically because it's dealing with power 4. Let's take a look at this example. Here's the radius of this vessel is only 1, and of course here is 1 also. If I change this one from 1 to 2, or make this one from 1 to half, let's see how the resistance is going to change. The resistance of this one, when it's going to change from 1 to 2, the resistance is going to decrease by 16 times because of power of 4, remember? And if you decrease the size of this radius from 1 to half, the resistance is going to increase by 16 times. So changing diameter is a big player. Although it's not the only player, but it's a big player. As you can see, length has a role also with eta. So if I want to decrease the resistance in an organ, can I cut the vessel short to decrease resistance? That doesn't make sense. But the best way to change resistance would be changing the R. We give medication to the patient that is going to make the vessel to constrict or relax. As a result, my resistance is going to change by power 4, and as a result of that, Q is going to change. So imagine when my resistance is going to change dramatically, my blood flow is going to change as well. This is a simplified version of a big formula that is called Poiseuille's law. I'm sure I'm pronouncing it correctly, but this is a French name of the person who described this formula. But the point here is that the resistance is related to length of the vessel, to viscosity and radius. So what is viscosity? It's about thickness of the blood. Imagine if you spill water, it's going to flow. If you spill syrup, it's going to flow very slowly. When the viscosity goes up, when the blood gets thicker, then blood flow is going to slow down. We talked about the thickness of the blood before in the blood section. The most important player to increase the viscosity or thickness of the blood would be hematocrit, would be the number of the RBC. If your hematocrit increase, if the number of the RBC increase, your blood is going to get thicker. So one of the things you can do to decrease resistance is removing red blood cells. Again, is this practical? Probably not. The most practical way would be changing what? Radius. Now, we mentioned that when the blood comes to the aorta, it's going to go to different arteries. So that is going to be the parallel pattern. But when blood is going to come to this artery, from this artery it's going to go to arterial, it's going to go to capillary, and it's going to go to the venule. So blood flow inside each of these organs would be in series. However, in different organs would be in parallel. As you remember in physics, we have two different setups for resistance. Resistance can be in series or can be parallel. Here, as you can see, they're parallel, but inside of each organ would be in series. What I mean by that is this. Let's say this blood is going to come inside the kidney. Let's make this kidney bigger. When this vessel is going to bring blood inside the kidney, which is called renal artery, this renal artery inside the kidney is going to change to arterial, which is smaller, and then it's going to change to capillary, and then it's going to change to venule, and then it's going to change to vein, it's going to get out, yes? So as you can see, inside the kidney, we have resistance after each other. Blood is going to come inside the artery, it's going to come inside the arterial, it's going to come inside the capillary, venial, and then vein. So inside the organ, we have a bunch of resistance in series pattern. Why is it important to know if the blood is going to flow in the series system or in the parallel system? Because, as you remember, if the blood flows in the series system, the total resistance would be the combination of those smaller resistance. So the total R would be R1 plus R2 plus R3 plus R4 plus R5. See, blood is going to come from the artery to arterial to capillary to venial and to vein. So when the blood is going to go through this series of the vessels, each of these vessels is going to have its own resistance. But when the blood is going to come through the aorta, it's going to go to this parallel of the blood vessels, then the total amount of resistance here would be 1 over R plus 1 over R2 plus 1 over R3 and so on and so forth. I'm sure you realize that in the series system, the total amount of resistance would be bigger than each of these single one. You have to add them up. So the total number is going to get increased. But in the parallel system, let's say if you have 4 different vessels, each one with a resistance of 10, the total R would be 1 over 10 plus 1 over 10 plus 1 over 10 plus 1 over 10. So now, as you can see, my total R would be 2.5, which is much smaller than every individual resistance. Now, the beauty of the parallel system is, if you add another resistance to this parallel system, instead of 4, now we have 5 of them. Again, as you can see, the total resistance is going to decrease. By adding more resistance to the parallel system, the total resistance is going to go down. However, let's say if you have 4 different vessels and one of them is going to create clot and the resistance here is going to go up. When the resistance inside one of these parallel systems is going to go up and it's going to get closer to infinity, that means blood flow is going to stop. As you can see, that is going to change to 0. That means now we are removing one of these parallel. Now we are dealing with only 3 of this resistance because 1 is gone, and as a result, your resistance is going to go up. So my point is this: by adding resistance to series, the total resistance is going to go up. By adding resistance to the parallel, total resistance is going to go down. But if one of these blood vessels get clot, that means you're removing one of this one. Therefore, the total resistance in the parallel system is going to increase. That's why if you have a clot in your coronary system, the resistance in your whole body is going to go up. As a result, R is going to increase. Then the blood flow is going to decrease in the whole system. So don't forget that. And the last thing I want to tell you about the series system versus the parallel system is this. Blood flow in the series system is the same. Blood flow in the artery and arterial and capillary and venial and vein would be the same. In the case of my kidney that I explained, blood is going to come to the renal artery, is going to go to the renal arterial, is going to go to capillary, is going to go to venial. The blood flow is going to be the same. But the pressure in each of this one is going to drop because as the resistance increases, the pressure is going to drop. However, in the parallel system, you have to realize the blood flow in each of this circulation would be a fraction of the total blood flow. So let's say out of 100%, we said 15% is going to go to the brain and 5% is going to go to the coronary. So out of the total blood flow, each of this system is going to get a fraction of the blood flow. However, the pressure for beginning of each system would be the same. And that is going to bring us to a different type of blood flow. We have 2 different types of blood flow. One is called laminar blood flow. A laminar blood flow is a blood flow that blood is going to flow inside the blood vessels smoothly. Like this shape is called parabolic. The idea is in the laminar blood flow, blood is going to move smoothly and the blood in the center of this stream has a highest velocity because the blood that's closest to the wall is going to create more friction, it's going to slow down. So that is going to create a parabolic shape. However, there's another type of blood flow, it's called turbulent blood flow, that blood is going to go in different direction. And as a result, you're wasting a lot of energy here. We want our blood flow to be laminar, not turbulent. If you put this stethoscope, if you grab a stethoscope and put it in any of your vessels, hopefully you're not going to hear any sound because blood is supposed to flow inside your blood vessels very smoothly without making any sound. When the blood becomes turbulent, then you're going to hear sound. It's called murmur. And we don't want to hear murmur because if you hear murmur, that means the blood flow is turbulent. What is going to make this blood to become turbulent or laminar? To determine the blood is going to be laminar or turbulent, we use a Reynolds number. We can calculate the Reynolds number, and if this number is 2000 or higher, the chance of turbulent blood flow increases. The higher than 2000, the better chance of turbulent flow. When the number is less than 2000, the chance of laminar is going to increase. To measure Reynolds number, there are different factors, but the most important factors would be viscosity and velocity. The Reynolds number can be measured by this formula, and that is rho times d times v divided by eta. Eta is viscosity, so when the viscosity goes up, the Reynolds number is going to go down because it's going to slow down. When the velocity goes up, the Reynolds number is going to go up. Also, diameter would be important. Now you have to pay attention. This is going to be very interesting. When the diameter decreases, the Reynolds number should go down. However, when the diameter goes down, the Reynolds number is going to go up. Why? Well, this is a really interesting point. Let me repeat one more time before I tell you why. The Reynolds number depends on few factors. The most important one would be the velocity and viscosity. When the viscosity increases, the Reynolds number is going to decrease because blood is going to move slowly. When the velocity goes up, the faster the blood is going to go, the better chance to create turbulent blood flow. Diameter, when decreases, the Reynolds number should go down, but you will see when the diameter goes down, the Reynolds number goes up, and that is confusing. But the reason for that is very simple, because remember when diameter or radius goes down, my velocity is going to increase by power 2. So as a result, the radius has more effect on the speed. When the radius goes down, the velocity is going to increase big time, that as a result, the Reynolds number altogether is going to go up. Make sure you understand, when the radius goes down, your Reynolds number doesn't go down because decreasing the radius is going to increase your velocity. So when you decrease the radius, your velocity is going to go up, and as a result, when the velocity goes up, your Reynolds number is going to go up. The next term that you must understand is called capacitance or compliance. We're going to talk about this one in the respiratory system again, but you have to understand the capacitance or compliance basically means the amount of blood that a vessel can hold at any specific pressure. How much volume you can hold inside the vessel at any given pressure. Vein has the highest compliance. Vein are the one that hold a lot of blood versus artery. Artery has less compliance or capacitance. At any given pressure, you can hold more blood inside the vein. Therefore, we say the higher the compliance of a vessel, the more volume you can hold at any given pressure. The compliance depends on distensibility. The better you can distend the vessel, you can expand the vessel, the more blood you can keep inside the vessel. That means your compliance is higher. Take a look at this diagram. Forget about this one for now. As you can see, at any given pressure, the vein is going to hold more blood compared to artery, because artery has low compliance, but vein has a higher compliance. In a very low pressure, as you can see, vein can hold a lot of blood. As you get older and older, your vessel is going to get more stiff. And as blood vessel is going to get more stiff, that means less distensibility of the vessels. If the vessel is going to get less distensible, that means now you have to put more pressure to keep these vessels open to make sure blood is going to stay inside the artery. In other words, if this is your heart, and this is again your aorta, my left ventricle is going to push the blood inside the aorta, and the aorta should accommodate, should open up. If aorta becomes stiff and lose the sensibility, so when my heart is going to pump to push blood inside this aorta, and if the aorta doesn't expand well, that means I have to push even harder. That means I have to increase my pressure to open up this aorta. As a result, I would say the compliance of the vessels as you get older is going to decrease. And as a result, your heart must work harder to push this blood inside the aorta, because aorta is not accommodating, is not expanding. That would be very important. So as you can see, as you age, your compliance is going to go down. So I hope you understand why when you get older, your arterial blood pressure is going to increase. In a normal person, we are not talking old or diseased person, in a normal person, the highest compliance in the arterial system, it would be inside the aorta. Why? Because again, when the heart is going to contract, it's going to push this blood inside the aorta, and if aorta doesn't have a good compliance, cannot open up and accommodate for this blood.